it slightly. Yeah. All right, so a couple people out now. All right. So right south. So it'll get worse with time. Something to look forward to. Questions to hear? All right, so that's two free ends. Obviously, the one that we haven't dealt with yet is one fixed, one free. In other words, what it's going to be is going to be a tube where I have one end blocked and the other end is open. We just happen to have one right over here. Now the pattern is going to be a little bit different. So if I have one fixed, one free end, or one open, one closed end, so one fixed, one free. A fixed end, node or anti-node? No. And a free end? People said it very quietly though. With confidence, with feeling.
Anti-node.
There we go. A lot of feeling in that. So what's going to happen is that when I hit a resonance, like the simplest pattern is like this. So the first question is, how many waves is that?
Like a quarter.
It is. So whatever the distance is from here to here, that length is equal to a quarter of a wave. Another way you can look at it is it's basically half of that. So half of a half, which is a quarter. And so 4 times that length is equal to the wavelength. This is the first harmonic, as hopefully you would expect. Now the next harmonic, again, we add a half wave every single time. So the next harmonic, again, I have a node at one end and an anti-node at the other. How many waves is this?
1, 7, like 3/4.
Yeah, it's 3/4. I have a quarter and then I add a half, which is 3/4. The math is throwing you. Think of if you have 1/4 and then someone hands you 2 more quarters, you got 75 cents. So that's 3/4 of a wavelength. Now this is where the pattern might seem to fall apart here. This is actually the third harmonic. So over here, L is a half of a wavelength. The second harmonic is twice that. The third harmonic is 3 times that. L is 3 halves of a wave, and so forth. Same over here. First harmonic, I have a half of a wave. Next harmonic, I have 2 halves. Then I have 3 halves. Then I have 4 halves. So the harmonic is whatever number you're multiplying times a half, whatever times the base. So since I have a quarter here, and this is 3 times that, it's called the third harmonic. If you look at some of my older tests, I might call it the second harmonic by mistake, and then I got convinced later. But this is the third harmonic. The next one we would hear would be the fifth harmonic. Again, node, and I added too many. That was the 7th harmonic. There you go. And since that is the 5th harmonic, it's that distance from there to there is going to be 5/4 of a wavelength. Just because you might see the language somewhere, and I think I probably mentioned it in the video on this, to get away from the skipping the even harmonics, that sometimes they'll call it the fundamental frequency, and then the first overtone, second overtone, third overtone, as opposed to first harmonic, third harmonic, fifth harmonic. I tend not to use the term overtone, but you might run into it. what would be the length of the seventh harmonic? How many wavelengths is the seventh harmonic?
One and three quarters.
Okay. Yeah, or 7 quarters. So let's make some predictions. I have a tuning fork which plays a frequency of 256 hertz. So this time I know the frequency. What I'm going to be doing is predicting the length. So my frequency, 256 hertz. I know the speed of sound, at least roughly, 340 meters per second. So I want to figure out the wavelength. What wavelength is being produced by a 256 hertz frequency? So the wavelength, I know frequency times wavelength is equal to speed, or the wavelength is speed divided by frequency. So 340 divided by 256. Units?
Hertz.
Wavelength.
Meters.
Yep. All right, so a little over 4 feet. Because when I produce the sound, that tuning fork is vibrating back and forth, and it's basically pushing air out. It's a longitudinal wave. It pushes air out into a high pressure area, and then, or compression. Then when the tuning fork bounces back, it creates a small, slightly vacuumed area, which is called rarefaction. And then it goes back and produces higher pressure, then lower pressure, higher pressure, lower pressure, vibrates back and forth. And the speed is traveling at 340 meters per second, so by the time the tuning fork gets back to the original position, that wave has traveled 1.328 meters.
Is there any way you can like measure that?
Beyond what we're about to do, there's probably some nice slick little way of doing it, but. Oh, well, actually, there's a special name for it. I can't remember what the name of it is, but you take a long tube with holes in it in the top. So like a metal tube, closed at both ends. You pump gas into it and then light it. So you basically have flames at set intervals. Then when you play if at one end you have sort of a rubber diaphragm, not at the end where the gas is coming in, and you play sound against it, that's going to vibrate at the rate at which the sound is hitting it. And what you'll see is these sine waves showing up in the flames. We do not have one of those. We have these. So we don't get the visual of the whole thing, but we'll make a prediction about where we'll get an antinode at the top. So for the first harmonic, I know that the length is 1/4 of the wavelength. So for the first harmonic, so that's going to be 1/4 of 1.328 meters. So how long does our tube need to be? Like 342.
We're at 332.
332. That makes more sense. All right, units?
Meters.
Yep. All right, so I would expect the first harmonic to happen when the water level, so looking at this, we have our open end, our anti-node, and our closed end right here where it hits the water, because the air can't go past the water significantly, and so that would be a node down here. So the air molecules basically stop moving here. And so when the water level drops to 33.2 meters, we should get an antinode at the top and a node down at the bottom. Now the question is, if I have an antinode at the top, what does it sound like? An antinode?
Oh, yeah.
Antinode is when you have the biggest swings in pressure. What do you think would happen if you got your eardrum there and you get hit by high pressure, by high pressure, and then almost no pressure, and then high pressure again, as opposed to gets hit by low pressure and then not as much?
Like a ringing sound?
Not necessarily ringing is what I'm going for. Imagine you have a drum in front of you, and you got the drum skin there, and you tap it lightly or pound on it. What would be the difference?
The level of noise.
Yes. So when I've got the highest change in pressure, I'm going to hear the highest sound, or the loudest sound, I should say. Better wording. So I'll take our tuning fork, which I did something with. There it is. Now, whenever you are striking a tuning fork, please don't bang it on something hard. That's why we have these right here with the mallets. Occasionally, yeah, accidents happen and you get metal striking metal, and you can see some dings in this one already from that happening. So try to avoid that as much as possible. Can everyone hear that? Or is there anyone who can't hear that? Or could not hear that? So what I'm gonna do is I'm gonna put this over the tube right here. As the sound's basically going down, bouncing back and coming back. As the water level gets to the right spot, it is going to, well, we'll get the perfect resonance, or it's physics, not perfect, but we'll get a resonance, and we should get the antinode at the top. Before then, it's sort of jumbled and we don't get that louder sound. Now we're gonna adjust the level of the water by adjusting this. This is the reservoir. I have water in here that right now is about this point. If I raise it, if I bring this up, which it doesn't seem to want to move up, as I bring it up, the water level should rise. As I lower it, the water level should drop. And basically this will go down, that will come up until they're the same level. So, because we have the same air pressure on both of them right now. The other thing about this is that the measuring tape starts 2 centimeters from the top. So whatever measurement we get on here, I'm gonna add 2 centimeters to it. Not 100% sure why they gave it to us with not 0 at the top, but maybe for us to cut off, or there's some physics that I can't find, but I can't find any reason why they started 0 here or not here. So we'll add 2 centimeters to what we get. So I would expect it, I'm expecting around 33 centimeters plus and then subtract the 2 there and I get 31. So somewhere around here I would expect it to be the loudest. The other thing I'm gonna do is, because the water level in here is rising, sometimes we hit a situation where we have to dump water quickly. So that's what this is here for. Let's find out if I can do this. Oops. So I'll start it up here. It's the loudest, looks like about 30.3. So this was predicted, and this was experimental. So we're about 10% off. Now the next harmonic. Well, let's make that prediction. At this point, I probably will have to dump water. Questions to hear before we predict the next harmonic?
When you did the 30.3, did you add the 2 centimeters extra?
Oh, I did not. Thank you. I feel like I'm usually more retentive about that. So 32.3. So we are even closer. So we are off by 0.009 divided by the prediction 0.332 times 100%. Yeah. Not bad. Thank you, Levi. All right, so our next prediction is my wavelength is not changing there. So what is changing is the length. So we'll go for a different color. Just let's see if that makes any difference. Oh, on the marker. That's one of the problems. So L2, for my my third harmonic, I know that L is 3/4 of the wavelength. So 3/4 times 1.328 meters, which should be somewhere around 0.996.
That's not enough.
Okay, units?
Meters.
All right, so 0.996 is going to be down here, and this will indeed, we will lose the mess of water when we do that. 0.996 is, yeah, down there. So we'll pull this up. And I will say this makes for a compelling video because I'm completely off screen here. All right, the water level is dropping here until it reaches the same level of the water in the reservoir. So that's going up, that's going down. Did somebody say something? Or I probably just heard that scraping against the table. All right. If you do it right, you get that wonderful metal on metal scraping. That's horrible. Too faded. All right. Never can't seem to get enough sound for doing it, cutting it in here. But that water level's not changing. Which means I put a crimp in the hose here. Wow, I'm getting nothing here at all. Alright, so I'm below the prediction. Prediction's usually much better. Did I make a math error? No. 0.996 meters. Well, that is sadly disappointing. I'm gonna get a different tuning fork. The tuning fork's not broken, just for some reason not here. Or could you hear it? Get a little bit louder? All right, I'm just gonna let the video run.